Suppose you have a function that adds 5 to each input. So when you put a 2 into this function, you get out a 7. Put in a 4, you'll get out a 9. If you put a 6 into this function, what do you get? Right, this output is 11. Now, one way you can write this function is to say that y equals x plus 5. So take any input, like the 4 over here. Plug it in for x in the equation up here, and that gives you the output y. 4 plus 5 is 9. So this equation represents the function that adds 5. How would you write out a function that adds 8? Here's a table with some inputs and outputs for the function. You'd write it as y equals what? Nicely done. So the function that adds 8 to an input can be written as y equals x plus 8. Next, how would you write a function that subtracts 2? Here's a table for this function. You can write it as y equals what? Exactly, you can write it as y equals x minus 2. Now, another way to write a function is like this, replacing the output y with this notation. And you can read this aloud as f of x. This function that subtracts 2, we're calling it f. So the way to read this is that f takes an input of x and gives an output of x minus 2. So this function f subtracts 2. Next, try writing a function that multiplies by 3. Here's a table with some inputs and outputs. If we call this function f, then we can write it as f of x equals what? Excellent. So f of x equals 3 times x, which you can also write as 3x. This function f multiplies inputs by 3. Next, how can you write a function that squares numbers? Let's call this function g, another letter that's commonly used to represent functions. So here's a table with some inputs and outputs for g. You can write this function as g of x equals what? Nicely done. G of x equals x times x, which you can also write as x squared. Okay, now suppose you have the function f of x equals x squared plus 3. So this function takes an input, squares it, and then adds 3. When x equals 0, f of x equals 3. See if you can fill out the remaining outputs of this table. Great, so here are the missing outputs. Now we said that when x is the input, f of x is how you can write the output. So when the input is 0, another way to write the output is like this, f of 0. So for this function f of 0 equals 3. And when x equals 1, we get an output of f of 1, which you found equals 4. F of 2 equals 7, and f of 3 equals 12. Suppose you wanted to evaluate f of 5. In other words, what's the output of this function when the input x equals 5? Well, we can plug in 5 for x. So we have 5 squared, then plus 3, giving us 28. So for this function, f of 5 equals 28. See if you can evaluate f of 8. Nicely done. So f of 8 equals 8 squared plus 3, which is 67. Next, try looking at another function, which we'll call h. h of x equals 4x minus 5. Go ahead and evaluate h of 1 and h of 3. Excellent. So h of 1 equals negative 1, and h of 3 equals 7. Finally, suppose you have the function g of x equals 2x. So this function g multiplies inputs by 2. For this function, see if you can figure out the missing inputs for this table. In other words, to get an output of 4, you should plug in 2 for x. What values should you plug in for x to get outputs of 6, 20, and 0? Nicely done. These are the numbers that, when you multiply them by 2, give you the outputs over here. Let's talk about continuity and smoothness. How shall we proceed? Okay, we'll start with continuity. A function is continuous if you can draw it without picking up your pen. So here's an example of a continuous function. It's continuous because you can trace the function in a single motion without picking up your pen. Now let's look at a few more graphs. Which of these shows a continuous function? Right, this is the continuous function. Here's a function that's not continuous because it has a break over here. Any place where a function is not continuous is called a discontinuity. Next, let's talk about smoothness. A function is smooth if it's continuous and doesn't have any pointy corners. Take a look at this function. It's continuous because you can draw it without picking up your pen, but it's not smooth because it has a pointy corner over here. Here are a few more functions. Which of these is a smooth function? Exactly. This function down here isn't continuous, so it can't be smooth. And these two functions on the right both have pointy corners. This was the only smooth function among the four. Let's quickly review continuity and smoothness. A function is continuous if you can draw it without picking up your pen. Here's a continuous function. This function, however, is not continuous because it has a break in it. Places where functions are not continuous are called discontinuities. And a function is smooth if it's continuous and doesn't have any pointy corners. Here's a smooth function, but this function over here is not smooth because it has a pointy corner. Let's introduce a few different ways to describe functions. They can be positive, negative, increasing, decreasing, and monotonic. They can also have maxima and minima. Click here if you're ready to learn about these different properties of functions, or if you already know about them, then try answering this question. Great, but first let's make sure you know what a continuous function is. Which of these graphs shows a continuous function? Right. Now let's say what it means for functions to be positive or negative. A function is positive where its outputs are positive, and negative where its outputs are negative. Let's see what that means graphically with this function here. Outputs are represented by y-coordinates, so the function is positive wherever its y-coordinates are positive. That's this part of the function here, above the x-axis. And a function is said to be negative in the places where it's below the x-axis. Let's look at another function. Where is this function positive? Now it's time for you to make your own function and see where it's positive or negative. To make your own function, drag anywhere on this graph. Regions that are positive are shown in green, and regions that are negative are shown in red. Try making a function that has exactly 3 positive regions. Let's take a closer look at what's happening between the positive and negative regions. This function here is continuous, meaning you can draw it without picking up your pen. Try changing this function around. For any continuous function, what's the output between positive and negative regions? Let's move on to when functions are increasing and decreasing. The real question we're asking here is this. As you increase x, what happens to y? A function is increasing if y goes up, and it's decreasing if y goes down. Let's see an example. We'll start with a point over here. As we increase x, notice that y is going down, so the function is decreasing. Over this next region, y is going back up, so the function is increasing. Over here, y is going down again, so the function is decreasing. Then it's increasing again, and finally the function decreases at the end. Now it's your turn. Here's another function. Where is this function decreasing? Nicely done. Now if a function is always increasing, then it's said to be monotonically increasing. Take a look at this function. If we start with a point over here and start increasing x, then y is always increasing. This function is increasing everywhere, and so it is monotonically increasing. Similarly, if a function is always decreasing, then it's said to be monotonically decreasing. If we move along this function, we can see that it's decreasing everywhere, and so it's monotonically decreasing. Here are 4 more functions. Which of these is monotonically increasing? Okay, it's time to make your own function again. You can change this function by dragging anywhere on the graph. This time around, the increasing regions are shown in green and the decreasing regions are shown in red. Try making a function that's monotonically decreasing. Suppose you have a continuous function that increases and then decreases. What happens in between? Let's start off with a picture. Here's a function, and it increases on the left and then decreases on the right. What can you say about the function between the increasing and decreasing regions? Exactly. The function has a maximum value, or highest point. This maximum point is called a local maximum. It's called a local maximum because it's higher than any nearby points. Take a look at this function. This one has 3 local maxima, over here, here, and here. The highest point for the entire function is called the global maximum. Next, let's switch the order here and see what happens. If a continuous function decreases and then increases, what happens in between? Now that you've seen a few local maxima and minima, try making your own function here with exactly 1 local maximum and 2 local minima. Excellent work. Let's quickly recap a few different ways to describe functions. When a function's output is positive, meaning it's above the x-axis, we say the function is positive. And when the output is negative, the function is negative. As x increases, if y also increases, then the function is increasing. And if y decreases as x increases, the function is said to be decreasing. A local maximum is where a function is higher than its surrounding points, and a local minimum is where it's lower than the surrounding points. Local maxima and local minima together are known as extrema because they're the extreme highs and lows for different parts of the function. If a function increases everywhere, then it's said to be monotonically increasing. And if it decreases everywhere, then it's said to be monotonically decreasing. So that's a whole bunch of ways to describe functions.